Assalamu alaikum everyone. Welcome to my second video of power electronics series. In our previous video we talked about how we can convert one level of DC voltage to another level, and we different circuits and their different properties. So today we would be talking about the very basic element of power electronics, or the very basic converter, which is called buck converter. And then we will see how buck converter is used to change a value of voltage to another one. And then we will talk about the steady state, and then after that we will talk about volt second balance and charge balance. Right. So in our previous video we saw that if we have a voltage source and we attach a switch, and it is on for some time period and it is off or at position 2 for some time period, then the output voltage is like this. The total time period is Ts and the duty cycle is D. Sorry, the total time is Ts and this amount of time is dTs. The D tells us the duty ratio. So what is duty ratio? Duty ratio is for the amount of time the signal level is high. So this amount of time is dTs and this amount of time will be 1 minus D into Ts, because this whole time period is 1 or Ts, right? So let's start how we can build a buck converter. So in previous video we also talked about there were switching, like as we see here, there is a switching happening at this point and we don't need this kind of voltages at our output stage. So we need some form of low pass filter which can filter out high frequency elements and give us a steady state or steady DC voltage at the output stage. So at this point we need to attach some low pass filter which can filter out high frequency elements. So the basic circuit of buck converter comes out to be like this. We have a voltage source, we have a switch, and then we have a low pass filter. We have inductor and capacitor, and then we have our load, right? So now the question is, how will it work? And in order to understand its working, we will do different analysis and we will see how does it change one form of voltage to another. Now if we look at the circuit of buck converter, we see that there are two switching positions, 1 and 2. So when our switch is at position 1, we see that this is our circuit. We have inductor in series, so there are different things that need to be kept in mind, that when we are talking about inductor, we need to measure its current, and when we are talking about capacitor, we need to measure its voltage. So at position 1, the voltage across inductor is equal to Vg minus Vc, right? And we know that VL, or the inductor voltage, is equal to L DIL by dt, that is equal to Vg minus Vc. And from this equation we can easily find the value of di by dt, that comes out to be Vg minus Vc over L. Now initially the rate of change of inductor current is 0, so some of this current will pass through capacitor and R0, which will start charging capacitor, and hence the capacitor voltage will start rising. Now when the switch is at position 2, we see that the circuit is this. We see that it is just like a parallel RLC circuit. So the voltages at inductor will be equal to the negative of, because initially this was positive and negative, and this inductor was in this way. So when this point is connected at this point, and then VL becomes equal to minus negative of Vc, right? Or we can say that DIL by dt is equal to minus Vc over L. Now we will see how does the output voltage and the inductor current changes with respect to time. So initially when the converter is not working, or it has just started, so the output will start increasing in this way, and it will reach at some steady state point, but the actual voltage will be like this. It will increase and then it will decrease, increase, decrease. There will be ripples on the output voltage, right? And when we see about the inductor current, it will increase, then it will decrease, it will again increase, and like this. And at the steady state, when capacitor is fully charged and inductor will have some initial value of current, the output voltage we see is like this, and inductor current has some initial value, and it will be rising like this, right? And we see that this slope is actually equal to, in our recently we derived the equation dIL by dt, that is equal to Vg minus dVg over L. So where does this dVg come from? We talked about that the output voltage remains at this point for dVg amount of time, or dVg amount of voltages, the amount for which it remains at position 1, and then it is 0 for 1 minus dTs amount of time. So from this point the slope is equal to Vg minus dVg over L, and this slope will be equal to minus dVg over L. From this equation we see that this the derivative of current over with respect to time is equal to 1 minus d into Vg over L, and 1 minus d is actually equal to d prime. We just name it as a d prime. So we see that the inductor current is changing in this fashion. Its rising slope is equal to d prime Vg over L, and its falling slope is equal to minus dVg over L. So from this diagram we can see that the net change in inductor current rise and fall is equal to 0. So this thing is actually volt second balance. So let's say at this point the inductor current is at Ts, and this point is inductor current at 0. So if we want to find the change, that is Its minus I at initial point, that comes out to be equal to 0 to dTs, because this point is dTs and this point is Ts, the total time period, and this thing is equal to d prime Vg over L dt, and dTs to Ts minus dVg over L dt, right? So after putting the values, we see that it comes out to be minus dVg over L times dTs. So minus dVg over L Ts plus d square Vg over L Ts, that comes out to be d prime dVg Ts over L minus dVg Ts to d prime over L, and that is equal to 0, right? Now this thing is called volt second balance. So similarly we have charge balance, in which the overall change in capacitor voltage is equal to 0, and this basically in power electronics or power converters we have to keep these ripples here, these ripple in some certain limits. We cannot change them, if this ripple will be greater than some value, then the output will be disturbed majorly. Now in order to measure the ripple magnitude of inductor current, firstly let us draw the inductor current waveform, and we see that this is the lowest point of inductor current ripple, and this is the highest point, and this is the midpoint, which is the actually the average inductor current. So the change in the inductor current is equal to delta IL. And similarly this point is also delta IL, and we knew this slope is equal to Vg minus dVg over L, or simply that is equal to d prime Vg over L. So in order to find the slope, we know the formula to the slope, that is equal to, slope is equal to rise over run. So we see that the slope is actually Vg minus V over L, and rise is equal to, this is our total rise from this point to this point, so that is equal to 2 delta IL, 2 delta IL divided by the run. We have the run from this point to this point, that is equal to dTs, so that is equal to dTs. So this is actually the magnitude of ripple that we are interested in. So that comes out to be delta IL is equal to 1 by 2 into Vg minus V over L into dTs. So this equation actually tells us how much is the magnitude of inductor current ripple. So we see that they have inverse relation, the delta IL has inverse relation with respect to L. So if we increase the inductor value, we can basically decrease the ripples in current, inductor current. So basically this is what we need in power electronics. We want the input current to be very smooth, so we have to use inductors of higher values. Now we will see how we can find the output voltages from, as we just discussed, that VL is equal to Vg minus V when the position when the switch is at position 1, and VL is equal to minus V when the switch is at position 2. So basically this is how it is. The output voltage, the inductor voltage is equal to Vg minus V, and for the next amount of time it is negative V. So if we just apply just integrate this area, we can easily find the output voltages. So by applying volt second balance, we can just easily find the output voltages. So by volt second balance, the output the inductor voltages in one time period is equal to 0. So this thing is equal to 0 to dTs to Vg minus V to dt plus dTs to Ts minus V dt. That thing is equal to 0. So from this Vg minus V dTs minus Vts plus V dTs, that thing is equal to dVg Ts minus dVts minus Vts plus Vdts. Cancelling out this, we see dVg Ts minus minus Vts is equal to 0, and from this equation Ts is also cancelled out. We see that the output voltage is equal to dVg. So we see that the output voltages are never greater than Vg, because D is always from 0 to 1. It is never 0, it is never 1. So actually this is a duty cycle which tells us how much time it is on and how much time it is off. So that's it for my side. So inshallah, in our next video we will discuss how we can increase voltages. If we have, let's say, 5 volts and we want to make 10 volts, 12 volts, even 50 volts, so how we can use boost converter to increase the input voltages to the desired output voltages. So thank you for watching this video. Please subscribe for more videos and give your comments in the comment section how you like my videos. Actually this is my first attempt. I'm making videos on YouTube, so and I'm also not that good in English. I'm just trying my best to deliver in the best possible way I can. So thanks, and please like